looking at Physics Paper 2, Variance 2, October, November 2023, AS Physics. The first question is in the following list, underline all the quantities that are SI base unit. Quantity that are SI base unit. Okay, so SI base quantity. Now, that's what are SI base quantity? They are the fundamental quantity with the fundamental unit. They are 7 number. Electric current is one of them. It's measured in amps. Time is one of them. The other one, force and charge. They are not fundamental quantity. They are derived. SI base quantity is also called fundamental. We reduce this. It's also called fundamental. Fundamental quantity. Yeah. Fundamental quantity. The same thing as SI base unit. Or SI base quantity, sorry. The next question. Under certain condition, the distance s move in a straight line by an object in time t is given by this. Where a is the acceleration of the object. State 2 condition under which the above expression apply to the motion of the object. Now, if you notice that originally the equation is supposed to be like this: s equal to ut plus half at squared. But now there's no ut there, which means most likely u is 0, such that s will now be 0 times t plus half at squared. And 0 times t is 0, so it's left up with this, which means that one of the conditions for which this expression can be used is that the car or the object starts with an initial velocity of 0 or start from rest. One of the conditions. Start from rest means u, which is initial velocity, with 0. Now the other condition we use this equation is that the object must be accelerating uniformly. The object is uniformly accelerating. So the equation of linear motion, v equal to u plus at, s equal ut plus half at squared, v squared equal to u squared plus 2 as are applicable when an object is accelerating uniformly or on a straight line or linearly. That is when you apply those equations. The next question. The variation with time t of velocity of a car that is moving in a straight line is shown. You can see the graph. It's a graph of velocity against time. The graph of velocity against time in most cases is always describing acceleration. So compare qualitatively the acceleration of the car at t equal to 8 seconds and at t equal to 14 seconds. Magnitude. Magnitude means the value in terms of the value and also in terms of direction. So at t equal to 8, this is at t equal to 8. So the object at t equal to 8 seconds, we have the same acceleration at t equal to 10. We have the same acceleration at t equal to 12. We have the same acceleration at also t equal to 4. Why? Because within this straight line, anyway, within this straight line, they'll have the same acceleration, the linear graph, so they have the same acceleration. So let me get the acceleration at t equal to 8. So I'll pick maybe 8 and any other point. You can also pick outside 8, it's not compulsory you pick 8. So at 8 seconds, it's easier for me to pick 8. Velocity is 10. And also at, let me pick another one again. Okay, let me pick here because they are still on the straight line. I'll pick between 12 and 8, and the corresponding velocity is 10 and 20. What's the acceleration? Change in velocity over change in time. So acceleration, what's the change in velocity between 20 and 10? That's 20 minus 10. The time is 12 minus 8. So acceleration is 10 over 4, which give me 2.5 meter per second square. That's the acceleration. If you pick any other point within this region, you're still going to get 2.5. You have to compare acceleration. This is when t equal 8 seconds. You have to compare with when t equal to what? 14 seconds. Now when t is 14 seconds, what's the acceleration? At 14, let me use another column. This is 14. At 14, what's the velocity? 10. Let me pick another point aside 14. Okay, at 14, it's 10. Let me also pick this because from here down the straight line is easier. Let me pick that. So acceleration in this case, is between 20 and let's say it's between 20 and 10, but it's decelerating. Instead of saying 20 minus 10, it's 10 minus 20 because it's coming down. We pick the final minus initial, 10 minus 20, and all the time is increasing. That one is not decreasing. So the time between both of them is 14 and 12. 14 minus 12. So here we have minus 10 over 2, which will give us minus 5 meter per second square. If you pick any other point outside my point that falls on this line, you're going to get the same thing. So let's give them. We just tell them at t equal to 8 seconds, the acceleration of the car is 2.5 meter per second square. At t equal to 14 seconds, the acceleration of the car is minus 5 meter per second square. That minus has already indicated that it's decelerating. Now direction. at t equal to 8 seconds, since the car is accelerating, you can say the car is pushing forward. You can say the car is pushing forward. That's accelerating. Y at t equal to 14 seconds. You can say the car is opposite of that, is pushing backward, or the car slows down. That is it. Now determine the magnitude of acceleration of the car at t equal to 4 seconds. 4 seconds at t equal to 4 seconds. This place. Remember, the car is it can be 2.5 because it falls between 4 and I think it's 2.5. Yeah. So because it's on the straight line between this and this, or let's look at it again like this. Let's look at it as if it's coming from -10 to 4. So in that case, so the change will be, acceleration. Let's confirm it. Acceleration is change in velocity over change in time. Change in velocity over change in time. At t equal to 4 seconds, since the car is accelerating. So at 4 seconds we have 0, and where it's coming from is -10, and the time is 4 and 0. So we can say v2, the final velocity, minus initial velocity. Initial velocity is 10. The time between them is 4 minus 0, so they have 10 over 4. You can see it gives us 5 over 2. It's still the same thing, provided that it's on the straight line, so they all have the same velocity as this. Can you see it here? So 2.5 meters per second. The third one, the car is at a point. The car is at a point t equal to 0. Determine the magnitude of displacement of the car from x. Displacement is change in position. Okay, let me clean this. Displacement is change in position. You have to determine the magnitude of displacement at t equal to 12 seconds. Okay, at t equal to 12 seconds. And what does displacement imply? Displacement implies total area under the graph, or area under the graph in specific. Maybe that condition. Whenever you hear displacement, it means area under the graph, if graph is given. So the question is displacement of the car from x to t equal to 12 seconds. Like I said, displacement implies the total area according to the question from t equal to 0 to t equal to 12 seconds. From t equal to 0 to t equal to 12 seconds. So from here, at 0, let's say this is A1, this is what? A2. So displacement should be area 2 minus area 1. I remember that area 1 is negative. So at the end of the day, the displacement will just be addition of the two areas. Remember that it's from 0 to 12 seconds. So which means that we are going to stop here. Let's find area 2 first. Area 2 is like a triangle. So the base of the triangle is 8, while the height of the triangle is 20. While the height is 20. So area 2 is half base times height. Like we said, the base is 8, the height is 20. 2 here and 2 here is 4. Area 2 is 80 meters. Let's find area 1. The base of triangle of area 1 is 4, while the height is 10. I've already factored in the negative from the formula. So half base times height, also area 1 is half base times height. I think the base is 4, the height is 10. 2 here 1, 2 here 2, or they have 20 meters. So the displacement, which is A2 plus A1, AT plus 20, the displacement is 100. That's it. Number 2, lately they've been setting questions on pressure upturns. Last May June exam, like two with all the variants, I think pressure upturns density question came out. So they are leaning toward that trend again. And the question is a high altitude balloon is stationary in still air. A solid sphere altitude is stationary in still air. Take note of that word, stationary. A solid is suspended from the balloon by a string. A solid is suspended by the balloon from the balloon by a string, as shown. Look at the string, this is a balloon. So the volume of the balloon is 7.5 meter cube. The total weight of the string, total weight of the string and the sphere, 65 Newton. Weight of the string and the sphere, which is still S, 65 Newton. The upturns acting on the string and sphere is negligible. The upturns acting on the string and the sphere is negligible. So calculate the density. Okay. Calculate the density of the air surrounding the balloon. Density of the air surrounding the balloon. Oh yeah, they said the upturns is negligible. Okay. Now let me draw the free diagram. This sphere, and there will be a weight down. In the air, there will be upthrust, but it is negligible according to the question. So calculate the density. Density is mass over volume. Density is mass over volume. Okay. Density of air is mass over volume. And since we are given weight, weight is mg. So the mass is weight over g. So density of air, what is the mass? Weight over g all over volume. So density will be weight over Vg in this case. The weight is 65 Newton. The volume is 7.5. G is 9.81. Density is 0.88. That's it. So the string breaks, releasing the sphere. Remember that if the string breaks, if the string breaks, and the sphere if the string break and the sphere is moving downward, you know, the string and the sphere are held together, so it's no longer attached to the balloon, it's moving downward. So state the magnitude of the acceleration of the sphere immediately when the string break. It's no longer attached to the this state the magnitude acceleration of the sphere. Yeah, the sphere is no longer attached to the string, so it's falling freely. So the acceleration at which the sphere is falling is gravity, 9.81 or 9.8 meter per second. So that's it, 9.81 meter per second. Because it's falling freely once it's detached from the string. The next question, state and explain the variation, if any, in the magnitude of acceleration of the sphere when it's moving downward before it reaches terminal velocity. Now, I'll start from here. As it's going down or downward, the acceleration, okay, let me start like this. Let me just nail it. The acceleration would be decreasing. Why? Why is the acceleration decreasing? You know why? Because air resistance, anyone they want to use, or drag force, or viscous forces, anyone they want to use, or viscous forces is increasing. Why is it increasing? Drag force is a function of velocity. I mean, drag force is proportional to velocity, because also the velocity is increasing. As it's falling down, velocity is increasing. You know that. Since drag force is a function of velocity, so drag force is also increasing. Drag force is the resistant force. You know, look at the balloon. The weight is constant. As it's falling down, the resistant force, as it's falling, maybe it's 10 Newton here. When it fall further, drag force increase. When it fall further, the drag force increase again. And remember that resultant force in this case is weight minus drag force. As the drag force is increasing, resultant force is decreasing. As the drag force is increasing, weight is constant. Resultant force is decreasing. Hence, velocity is also increasing, full stop. Hence, resultant force Rf is decreasing. Resultant force is the weight minus drag force. It's decreasing. From Newton's first law of motion, resultant force is decreasing and the acceleration will definitely be also decreasing. As stated earlier, decreases. Force is proportional to acceleration. At a point or a point, a point will be attained, will be reached let me use this. Now, there will be a point whereby the drag force will match the weight. As this continue, the drag force will match or equal the weight of the sphere. Will match or equal the weight of the sphere, which led to the resultant force Rf to be zero, and also acceleration at that point to be zero. At this point, the sphere will move with a terminal. Velocity. That's what happened. So I believe it's clear. As the sphere fall or keep falling, the drag force keep increasing. As the drag force increasing, the resultant force decreases, which leads to acceleration to decrease. There will be a point where the drag force will match or be equal to the weight. That point is called terminal velocity. That's what they want us to do. Like my little drawing from 10 to 15, from 15 to 40, like that. That's it. The sphere has a mass of 4 kg. Calculate the total resistive force acting on the sphere. Okay, like I said, resistive force opposing motion, the weight downward. There will be a resultant force when two forces are acting on an object. The resistive force minus weight. What are we looking for? We are looking for the resistive force. So from here, resultant force is mass times acceleration. I don't have resistive force, but weight is mg. So 4 times 1.9 plus 4 times 9.81 will give us resistive force. That's 7.6 plus 39.24. So we have 46.8. So 46.8 Newton or 47 Newton. That's it. Number 3. A vertical rod is fixed to the horizontal surface of a table as shown. You can see the vertical rod as shown. A spring of mass 7.5 grams is able to slide down the full length. You can see the string. Let me change the color. A string of mass 7.5 grams. Look at this string. The mass of the string is 7.5 grams. Able to slide down the rod. So the spring is first pushed against the surface of the table. Is pushed against the surface of the table like this. They push the string against the surface of the table with an initial compression. Compression, like compression is like extension. Initial compression, change in x, or this is 2.1 centimeter. So to meter, that will be 0.021 meter. That's they compress it down. You know, when they compress the string down with your hand, you are storing energy in the spring. Energy is being stored when you compress. When you also stretch a spring, you're also storing energy. Because you're still going to release, and the spring will fall back to wherever the spring is coming from. The spring is then suddenly released so that it leaves the surface. So now, when this is downward, is compression. So when the spring is released, it is released to move, right? To move upward when it releases with a kinetic energy. You know, release is moving, so it releases with kinetic energy of 0.048. If you remember, if you know what is happening, when it's released, it's moving the kinetic energy. At the same time, it's gaining height. You get, at the same time, is what? Gaining height. So assume the springs obey Hooke's law and the initial elastic potential energy of the compressed spring. Yeah, they said initial elastic energy. Look at the word initial elastic potential energy of the compressed spring is equal to kinetic energy of the spring as it leaves the surface of the table. Air resistance is negligible. By using the initial elastic energy of the compressed spring to calculate the spring constant, the condition is, since they've said it, since the elastic potential energy is equal to kinetic energy. What's the formula for elastic potential energy? Half kx squared. And the kinetic energy in the spring is 0.048. Or what are we looking for? Calculate the spring constant. Okay, let me make the spring constant a subject of formula. Since elastic potential energy, let me call it EPE, is half kx squared. Kinetic energy is already given. So I'm looking for the spring constant. K is the spring constant. So just let's do our math, this change of subject to formula. So from here, x squared equal to 2ke over k. So x, this compression or the extension, is 2ke over spring constant. K is spring constant. So x will be square root of 2ke. Ke is 0.048. Y, oh no, I'm looking for the spring constant. I'm supposed to make the spring constant the subject of formula. So the spring constant should be 2ke over x squared. Yeah. So spring constant is 2 times the kinetic energy is 0.048. Ys is 0.021 squared, the compression. So this will give us 0.096, 0.021 squared, 4.41 times 10 to the power of negative 4. So give me 0.022 times 10 to the power of 4, which is 1, 2. So 2.2 times 10 to the power of 2. That is spring constant. The next question, calculate the speed of the spring as it leaves the surface of the table. The spring of the speed as it leaves, it leaves with a kinetic energy of 0.048. It's easier. Kinetic energy is half m, is initial speed. So half mv squared equal to 0.048. So from here we have okay, half. Let me make v naught the formula. So v naught will be 2 times 0.048 divided by the mass. The mass is, I think we are given from the question. I saw 7.5 something. Yeah, 7.5 grams, the mass of the spring. The mass of the spring is 7.5 grams. That's 7.5 times 10 to the power minus 3. So the speed, the speed the spring using coming off the initial speed, 2 times 0.048, that's 0.96. Let me check it. 2 times 0.048, 0.096 over 7.5 times 10 to the power minus 3. 1, 2, 3. 0.096 can be written as 96 times 10 to the power minus 3 over 7.5 times 10 to the power minus 3. At the end of the day, I have 96 over 7.5, which is 12.8. So the speed at which this spring using leaving the surface of the table with given 3.58 meter per second. C question. The spring rises to the maximum height. The spring rises, I mentioned this earlier, rises to the maximum height up the road from the surface of the table. This causes gravitational potential energy to increase by 0.039. Remember that our former potential energy is 0.048. Do you know why? Because the question said initially potential energy, this is equal to kinetic energy. And kinetic energy, the table we use in living is 0.48. So our initial potential energy is 0.48. Now, the question said that when it leaves, the potential energy increases by this, which means that the new potential energy is 0.048 plus 0.039. It increases. So the new potential energy is 0.087 joule. That's the new potential energy. So the question asks us calculate this movement of the spring for this movement of the spring, the increase in height of the spring after leaving the surface. We have to find the increment in height after leaving the surface. Okay, after leaving the surface, we have to find the increase in height after leaving the surface. Okay, let's go back to the original question. Let's see something. So you can get something down from there. The spring is okay. Let me see. A vertical rod is fixed into the surface as shown. The spring of mass slide down the full length. The spring is first pushed down against the surface. It has initial compression. Yes, that's the word I'm looking for. The spring is suddenly released. It's suddenly what? Released so that it leaves the surface with this energy. It leaves the surface with this energy and with this speed. Yes. It leaves the energy with this energy 0.048. So now the fact that they use released, and it's going against gravity. Remember, v square equal to u square minus 2gs. It's going against gravity. It's released. U is 0, g is h to attain height. At the end of the day, I have is okay. Use the maximum height. Okay, let me look at it in this way. Spring rises to maximum height. Oh, okay, it's making sense now. It rises to maximum height. So v square at least this is correct. At maximum height, v is 0, u square minus 2gh. So I have u square minus u square equal to minus 2gh. Minus cancel what? Minus. So in this context, that height is u square over 2g. That height we are talking about. This 9 is not there. This is number 9. Sorry, page 9. Sorry, u square over 2g. Okay, that's what I'm going to use now. We have initial height and we have new height. So we said calculate the increase in height of the spring. So increase in height should be the new height minus initial height. New height, what the formula for height? That will be new velocity over 2g. The initial height, that will be old velocity over 2g. So which will give us 1 over 2g into bracket the new velocity minus the initial one. This is what I'm going to use. Now, since we have our new potential energy, which is this, and the question said potential energy equal to kinetic energy, that's the condition in the question. So 0.087 will be equal to half m v nu square. Okay, let me be using u so it won't confuse us. Nu square. So from there, I have the new velocity will be 2 times 0.087 all over our mass. Our mass has not changed. Nothing affects the mass. I think this one gives us 23.2. It gives us 23.2. So therefore, since the new one gives us 23.2, so when you find the square root, it gives us 4.82 meter per second. Now let's find the change in height. So the change in height will now be 1 over 2g.981. What's the new one? Un squared. That's 23.2. The old one, the initial one, let's look for it. Oh, that's 12.8. That's 12.8. So at the end of the day, when you do your calculation, 23.2 minus 12.8, I think it's 10.4. This one gives us 10.4 over 2 times 9.81. 2 times 9.81, 19.62. 10.4 divided by 19.62, we have 0.53. This is the increase in height. I believe it's clear and we all understand. So that's it. The next question. The next question. Calculate the average frictional force exerted by the rod on the spring as it rises. We have to calculate the average. This question is interesting. Student, you need to learn how to apply whatever you've been taught in class. These are simple applications. An interesting question. I'm enjoying it anyway. Provided the fact that there's no max team yet, but I can assure you this is 100% efficient and effective and correct. Calculate the average frictional force exerted by the rod on the spring as it rises. The average frictional force exerted by the rod on the spring of frictional force. So as it rises, frictional force as it rises is going against. As it rises, work is being done because there's change in height as it rises. So, this is good. Work done is first times this. Now, what kind of work is done? Okay, this is it. This is the work. It increases by this. When you subtract this 0.087 minus 0.048, when you subtract them, you're going to give you 0.03. Now, this is the work done called the frictional force. Frictional force. As it rises, the distance is 0.53. The change has to go with this. So frictional force, that's the change in energy over change in height. Yeah, that's it. Change in energy. Change in energy over change in height. My energy is the work done, the height is the distance. That's all right there. So 0.039 over 0.53. It gives 0.075 Newton. Perfect. That's it. Now the rod is replaced by another rod that exerts negligible frictional force. Okay. On the moving spring, the initial compression of the spring is now varied. The initial compression is changing. It's now varied in order to vary the maximum increase height. Okay. The initial compression, they are changing it. As they are changing it, the change in height will be changing. Of course, after leaving the surface. Assuming the springs obey Hooke's law, calculate sketch the graph. Okay, in this case, like they said, potential energy, elastic potential energy is equal to kinetic energy. No, in this case, no, this will not work. Changing height against x. Oh, okay. The graph is changing height against x. Okay, for the spring, this is what we're going to use, minus half kx squared. This is for the spring. The minus is now going against the, in the compress it down is released. So that's why I put the minus, showing that it's opposed the initial agreement. Let me use another color. Negative. This is for the spring. As it release is equal to, it's gaining height, mgh. As it also release, it can also be half mv squared, but the graph is about changing height against x, so I chose that mgh. So from here now, and remember that in this case, we are varying the height. So change in height. So I need to plot the graph of this against this. So from here, divide both sides by mg. Divide both sides by mg. Hold on. My laptop is acting up. Let's hold on for a few minutes to come back. Okay, welcome back. So I need to plot the graph of change in height against x. So divide both sides by mg. So mg cancel mg. So here I have half. So k over mg times x squared equal to change in height. The number is constant, half. K is constant, weight is constant. So all this is regarded as constant. All this is regarded as constant. So let me use that constant. Let me use them as okay. Let me use them as constant b. The minus is there. Bx squared equal to change in height. So now from here, change in height is proportional to x squared. So the gradient is minus b, is decreasing. So if you are going to sketch the graph of this, sorry, a minute. Okay, so if you are going to sketch the graph of change in height against x squared, that's the this is the model. I've already given the model, and from the model we have change in height proportional to x squared, and the gradient is negative, so it's going to be a parabola graph that is decreasing. A parabola graph that is decreasing. A parabola graph that is decreasing kind of have a negative a. Oh, they have, like, if you have minus ax squared plus bx plus c, the equation of x squared is negative, so your graph will be like this. your parabola graph is most likely be like this, right? So that's exactly what's happening here. So our parabola graph is like this. That's the graph. This is perfect. So let's move on. It's not a full parabola, so this is where you're going to stop. Next question, momentum question. The question is a ball Y move along a horizontal frictionless surface and collide with the ball Z in the view above is this. So ball Y has a mass of 0.2 kg and the line PQ in the direction PQ, horizontal direction. So Z is stationary. So Z is stationary. Okay. After collision, ball Y move with a final velocity at an angle 27 degrees to the line PQ, and Z at the final velocity of 5.5 at an angle 44 degrees to the line PQ, as shown. So 5.5 and that as shown. So calculate the component of final momentum of ball Y, in a direction perpendicular to PQ. Final momentum of ball Y, okay, this is ball Y, in the direction perpendicular to PQ. Okay, this is PQ, perpendicular to PQ is the vertical direction. So this is perpendicular to PQ. So we have, at the end of the day, we have something like this, perpendicular to PQ. This is what the axis to look for, the direction of final momentum. Let me find the vertical velocity according to what the axis to do. This place is 3.7 meter per second, and the angle is 27 degrees. That's it. 3.7, 27 degrees. I'm looking for this velocity perpendicular to PQ. This is PQ. Perpendicular to it is QR. Opposite over hypotenuse. So sine 27 is opposite over hypotenuse, 3.7. So velocity is 3.7 sine 27. So velocity of Y perpendicular to PQ. Let me be sure. Velocity of Y, is that the question? Yeah. Perpendicular to PQ is 3.7 sine 27. So sine 27 times 3.7. So 1.6. The velocity is 1.6798. Approximately should be 1.6. 1 point. Let's use 1.70 meter per second. So that's the velocity, but the axis to find the momentum. Momentum of Y after collision is mass times velocity of Y after collision. So the mass of Y, is 0.25. The velocity, let's use the original value, 1.6798 times 0.25. So 0.42. So the momentum after collision of Y in the direction perpendicular to PQ is 0.42 Newton seconds. The next one, by considering the component of final momentum of each ball, in the direction perpendicular to PQ, calculate MZ. The same thing, you want us to consider, so why is this one mark? I want us to consider this also, the component of the other momentum, this one, the component of this in this direction. You want us to consider it. So that one look like this, if I'm not mistaken. Yeah, the component is downward because this is PQ, and it's something like this. We have the angle 44 degree, and this point is 5.5. We check the question. What is it? So MZ is, the speed is 5.5. So let's get this component for VZ. Sine 44 opposite over hypotenuse. So VZ is 5.5 sine 44. So sine 44 times 5.5. So the final velocity after calculation of component of Z perpendicular to PQ is 3.82. 3.82. Okay. 3.82. So the momentum, the final momentum of Z after collision in that direction is mass times velocity. The mass is mz, I don't know, the velocity is 3.82. So the final momentum of Z in that direction is 3.82 mz. But the question asks us to find Z. Now, if you note this, this direction, the momentum we just look for are vertical momentum. That's for vertical. For Z is downward, negative. This is upward, positive. So, from the principle of conservation of linear momentum, momentum before collision in a vertical direction before collision is zero. There is no vertical direction before collision. So before collision is zero. After collision, we have 0.42, and it's upward, plus minus 3.82 mz, that's downward. From here, we have minus 0.42 equal minus 3.82 mz. Minus cancel minus. The mass of Z after collision is 0.42 over 3.82. So 0.42 divided by 3.82. So we have 0.11 kg as the mass after collision. Okay. Okay, that's it. Let me be sure we did the right thing. So component of y 3.7, the angle 27. Okay, the angle 3.27. So then this, and the mass 0.25. Okay, I think we are good to go. Now, during the collision, the average force exerted on y by z, I mean this, the average force exerted on y by z, this is what they mean, on y by z, I think is and the average force exerted by z on z by y, like this is what they are talking about. So compare the magnitude of Fy and Fz. Numerical value are not required, magnitude. Okay, if in terms of magnitude, the forces are equal forces or same forces. Direction, opposite direction to each other. This is Newton's third law of motion, to each other. That is the next question. Two blocks A and B move directly toward each other along the horizontal frictionless surface as shown in the view. So perfectly elastic. They collide perfectly elastic, which means that the relative speed of approach must be equal to relative speed of separation when they move in a particular direction. This is it. So in this case, U1 is 4. Okay, let me use it properly. U1 is 4 minus B is going in opposite direction. That's minus 6. So the question said the block A has a speed of 4 and B has a speed of 6. After collision, that's final. Block B moved back. It moved back along its original path. It moved back along its original path. So when it moved back along its original path, the final is B2 minus B1. They said it moved back. When something moves back, what does it mean? So it moved back along its original path. So the original path is the path you are looking at, right? So it moved back along its original path. Okay. After collision, with a speed of 2 meters per second. With a speed of 2 meters per second. This one is 10. Calculate the velocity of A. They never mention anything about direction of A. So when it's moved back along its original path. So this should be 2 minus V1. So we have V1 is minus 8. That shows the direction. So V1 is 8. That's it. It's moved back. Okay, yeah. If it's moved back, that's going towards the positive direction. I'm correct? Okay. I should read. Number 5. A beam of vertically polarized light is incident normally on a polarizing filter as shown in 5.1. The vertical polarized incident light beam, you can see it, is transmitted in the axis of transmission. So the transmission axis filter is initially vertical. The transmission axis of the filter is initially vertical. Okay. The transmission axis of the filter is initially vertical. It's important. The filter is then rotated to angle 360 degrees while the plane of the filter remains perpendicular to the surface of perpendicular to the beam. Okay. While the plane of the filter remains perpendicular to the beam. Sketch the graph of the intensity of light in transmitted beam through which the transmission axis is rotated. Okay, this is Malus theorem. And Malus theorem or Malus law, the formula is I equal to I naught cos squared theta. I naught is incident intensity, I is the transmitted intensity. So the law is about cosine. So If you are sketching any graph, you know, cosine graph look like this. Cosine graph starts from the axis. Usually look like this. But if it's cos squared theta, so which means, you know, usually have +1 and -1. But for cos squared theta, you know, because of the square, no more negative or positive. So this is what we expect to have. What is cos 90? Cos 90, cos 0, what's cos 0? Let's start from 0. Cos 0 should be 1. Cos 0 is 1, maximum. That's the maximum value for cos. Cos 90 is 0. Cos 180 is -1. Cos 180 is -1. But due to the square, -1 square, +1. Cos 270 is 0. Cos 360, I think it's 1. So if we are going to sketch the graph, it comes like this. That's the graph. Using Malus theorem or Malus law, I transmitted intensity equal to initial intensity cos squared theta. So that's it. That'll be the graph. Okay. Let me check cos 360. Cos 360 is 1. Yeah. And the next question. The intensity of light incident 7.6 is the incident intensity when the transmission axis of the field at an angle theta to the vertical. The light intensity of the transmitted beam 4.2 transmitted beam, which is also I. Calculate angle theta using the law, Malus law. Transmitted intensity equals to the incident intensity cos squared theta. So we are looking for theta. Transmitted is 4.2. Incident is 7.6 cos squared theta. So cos squared theta is 4.2 over 7.6. So from here, cos theta square root of 4.2 over 7.6. So which we have cos theta square root of 4.2 over 7.6. It was 0.7434. From there, theta will be arc cos of 0.434. So our theta will give us 41.98 degree, which is 42 degree. That's it. The next question, calculate what is meant by diffraction of a wave. Diffraction of a wave can be defined, or let's say this is the spreading out diffraction. This is the spreading out of a wave. The spreading out of a wave when it passes through an aperture. When it passes through an aperture is called a gap or a gap. That's it. C question. A beam of light of wavelength 4.3 times 10 to the minus 7. This is the wavelength lambda 4.3 times 10 to the minus 7. Is normally incident on a diffraction grating in air, as you can see. The third order diffraction maximum of the light is at an angle of 68 degrees to the direction of the incident. Angle of 68 degrees to the direction of incident. Calculate the spacing d. Okay, the relationship for diffraction grating is n lambda equal to d sine theta. D is the spacing. So D, the spacing, is sine theta, is n lambda all over sine theta. So the spacing, n is the order, and we have 3, third order. Wavelength, we are given 4.3 times 10 to the power minus 7 over sine angle sine 68. So that gives us 1.39 times 10 to the power minus 6. That is spacing. The next question, determine a different wavelength of visible light that will also produce maximum. That will also produce maximum at an angle. Okay, or visible light. Okay, visible light, LIGHT ranges. I think this is too thick. Bit. Visible light ranges from 400 nanometer, which is violet, to 700 nanometer, which is red, which can also be the same thing as 400 nanometer. That's 400 times 10 to the power minus 9, 4 times 10 to the power minus 9, which is the same thing as 4 times 10 to the power minus 7. So 700 nanometer is the same thing as 7 times 10 to the power minus 7, which means that our wavelength in this question must be in between 4 times 10 to the power minus 7 meter and 7 times. Anything, you must get a wavelength in between this range to confirm that is visible light. If you check the original question, the wavelength is 4 times 10 to the power minus 7 in between the range. 4.3, yeah, between the range. So now they want us to get a wavelength with the same angle. So it's the order that will now determine it. You know, n lambda equal to d sine theta. N is the order with the same angle. I'm looking for wavelength. Our spacing is 1.39 times 10 to the power minus 6 with the same angle sine 68, but the order. Since the maximum order is third order, let's try and use 2 first. Okay, 1.39 times 10 to the power minus 6 sine 68. It gives us 6.44 times 10 to the power minus 7, which is 644 nanometer. Oh, so it falls in between the range, 6.44. So it's correct. 6.44 times 10 to the power minus 7. Let's see if you use more than 3. 1.39 times 10 to the power 1.39 times 10 to the power of minus 6. Multiply by sine of 68 divided by 4. It gives us 3.22 times 10 to the power minus 7 is outside the range, so it's not possible with fourth order. So our best bet, the one I can see, is second order, 2. Give us the same wavelength. Number 6, electricity. A metal wire has a resistance per unit length, R over L of 0.92 ohm per meter. The wire has a uniform cross-sectional area. This is area. Calculate the resistivity. Now, what's the formula for resistivity? Resistivity is RA over L. So in this case, that's R over L times A. And R over L is 0.92. A is 5.3 times 10 to the power of negative 7. So at the end of the day, 4.88 times 10 to the negative 7. That was resistivity. And the next question. A battery of EMF E has negligible internal resistance is connected in series with fixed resistor and light dependent resistor. The resistance is 1.4, the light dependent resistance is 6.4. The voltage across the LDR is 6.4 volts. So it's connected across the LDR. So it's going to read LDR, not fixed resistor. Show that the current in LDR is this. From Ohm's law, V equal to IR from Ohm's law. So current in LDR will be voltage in LDR over resistor in LDR. Well, the voltage in LDR 6.4, resistor in LDR is 1600. So with our calc, 6.4 divided by 160 gave us 4 times 10 to the power of minus 3 amperes. Remember, you are not going to be awarded for the mark, the final answer. You are awarded for the step. It's a 1-mark question and the proof question, which you know the answer already. Calculate the number of free electrons in LDR in a time of 3.2 minutes. You know, charge is equal to current times time. And charge is also the same thing as number of electrons equal to current times time. So we are looking for the number of electrons, N, that will be current times time over electron. So the number of electrons will be current in the LDR is 4 times 10 to the power of negative 3 times 3.2 minutes, take it to seconds, multiplied by 60, divided by E. E is 1.6 times 10 to the power of negative 19. So what is N? So we're going to get this. Okay. Oh yeah, it gives us 4.8 times 10 to the negative of 20. Perfect. Calculate EMF. In this circuit, we have the EMF should be the voltage in the fixed resistor plus voltage in LDR. The voltage in the fixed resistor is current multiplied by the resistor. The voltage in LDR is 6.4. The circuit is a series circuit. The same current flow. So the current in LDR is the current in the fixed resistor. The current in LDR is the same current in the fixed resistor. And the fixed resistor is 1400 ohm plus 6.4. So this times this, we have 5.6 plus 6.4. It gives us 12. So the EMF is 12. Calculate, determine the ratio of power dissipated. Power dissipated in LDR is current in LDR square multiplied by resistor in LDR. Power dissipated in fixed resistor, current in fixed resistor square multiplied by fixed resistor. The currents are the same, they cancel out. So it's resistor in LDR. The ratio is resistor in LDR by resistor in fixed resistor. Resistor in LDR is 1600. Fixed resistor is 1400. Double zero cancel 0. 8 over 7. So the ratio is 8:7. Or 8 divided by 7. 1.14 or 1.14. We get the same thing. The next question, C. The environmental condition changes, causing a decrease in resistance in LDR. Okay. In B, the temperature of the environment does not change. State whether there is a decrease, increase, or no change. Like, we all know that LDR are photosensitive devices. photosensitive. They react to intensity of light. They changes the resistance depending on the amount of light falling on them. They change the resistance depending on the amount of light falling on them. So in LDR, as resistance from the condition there, they said the environmental condition causes the decrease in resistance. So resistance decrease means that on LDR, decrease in resistance means there is more light reaching the LDR. So which leads to increase in intensity. That's the meaning. More light. Decrease in resistance means we have more light, which leads to increase in intensity. So here it increases. It increases. What's the reason? The reason is more light. More light is reaching. More light is reaching LDR due to decrease in resistance. That's the meaning. That's the reason. Now, current in the battery. The current in the battery is not directly affected by decrease in LDR. No. Current has no. The current flowing in the circuit depends on the overall resistance. Current depends from Ohm's law. The current will be, in this case, will be E over LDR plus fixed resistor. So let's see what will happen to current. E is 12. The LDR has decreased from 16, maybe is now 600. Nothing happened to fixed resistor, it's still 16. Let's say this one is 400. So at the end of the day, we have 12,000. No, 2,000. 12 over 2,000. 12 divided by 2,000. That's 6. That's 6. 6 times 10 to the power minus 3. Compared to it increases. So compared to 4 times 10 to the power minus 3. So which means as the resistance of the LDR decreases, current also increases. You can see. So current increases. Current increases. Let me put the reason. The reason is the current flowing in the circuit. The current in the circuit. The current in the circuit depends on the overall resistance. Which includes resistance of LDR and fixed resistance. So from analysis, you can see what happens as resistance decreases, current increases. What I just did now. Current increases, sorry. And the next one, the reading on the voltmeter. The reading on the voltmeter. Oh, the voltmeter is the one that is connected across the LDR. So yeah, it will decrease because the resistance as decrease. Yeah, to decrease. This one is quite straightforward. Decreases because it's connected directly to LDL. So V equal to IR. Connected directly to LDL. It's going to read whatever value attached to it. A low resistance, low voltage. So that's it. The seventh question, which is the last one. In the following list, underline all particles that are not fundamental. That not fundamental means can be broken down. It comprises of different components. That's baryon and nickel. They can be broken down. So they are not leptons. Now, the nucleus of thorium decays by emitting alpha particles and beta particles. Beta negative. Remember that alpha particle is 4,2 helium. Beta particle is 0 minus 1. Beta negative. So determine it emits alpha and beta particle to form lead 206. Determine the number of alpha particles and the total number of beta particles that are emitted during the sequence of decay from the nucleus to form lead 206 from thorium. It's from thorium, so we have 230 thorium 90. According to the question, it gives us there's a certain number of alpha particle that is required and a certain number of beta negative particle that is required. So to form lead 206. This is okay. What is X? What is Y? So from here, let me see it. 230. Okay, let me do like this. 230 minus 206, 24. We see what I'm trying to do. The upper part, the reactant is 230. The product is RV X plus Y plus 206. So from here, X plus Y 230 it give me 24, which means whatever that is here on top must give me 24. Must give 24. So, and this is 0. Okay, I know what to do now. This is upper part. The down part, let's say 90 equal the down part, P plus, in fact it will be P minus Q equal to 82. No, plus 82. 90 minus 82, that's 8. So P minus Q must give me 8. Oh, the down part. This is the down part. Down. This is the upper part. So, okay, I think I have an idea of what is going on. Since the upper part must give me 24, so I'll put X as 6, 4,2 helium. Let me put this as, so the lower part must give me difference of 8. 6 times 2 is 12. So I have to do, yes, have to be 4 in such a way that the down part will give it minus 8. Plus, I think this is the answer. 82 lead. This is the answer. So the total number of alpha particle is 6, beta particle is 4. Check it properly. That's it. Now the next question. A basin has a charge of negative electron, where E is the elementary charge. The quark composition of meson include a charm antiquark. A charm antiquark. A charm antiquark is -2/3 electron. Charm antiquark is -2/3 electron. State and explain the possible flavor. Possible flavor. Flavor means type of other quark in the meson. That will give us, everything must give us -1. A meson with minus electron is generally a charm and antiquark. Meson are composite particles made up of quark and antiquark. It's made up of quark and antiquark anyway, yeah. You should note that mesons are made up of quark and antiquark, held together by strong nuclear force. So in this case, the whole idea is just this. The answer should give us -E. One of the variable is this. So the other variable to give me -E is unknown. It's simple. So -E plus 2/3E will give me the other variable. So -3E plus 2E/3 will give me x. So in this case, x is -1/3E. This is the other variable. And this one is called down quark. Yes, -1/3 electron is called down quark. The symbol for down quark is D. So this charm antiquark, the symbol is bar U. So if you do analysis, let's confirm it. If you do -1/3E and -2/3E together, it's going to give us -3E/3, will give us -E. So which is correct. So which means that so state and explain the possible flavor of other quark in the meson. So the possible flavor, let me see, the possible flavor is D, the down quark. Sorry, the down quark, which is -1/3 electron. So this type of meson is composed of this, the anti-charge quark, and this. That's the answer. Oh, this is the end. I believe it's clear. If you have any questions, just send in the comment section. I'll see you in the next video.